Oh yeah, who knows what's going on with the overall grade?
Yeah. The 4 class average, right? The solid 4.
Which we do not hold it against you in any way, shape, or form. We know it's Blackboard. Blackboard is a piece of crap. It is a piece of crap that really enjoys messing with us.
Yeah. What's strange is like for my 200 level class, like it's been giving everybody like random grades. So like there's a whole random distribution in there. I don't know how it determined that. But in this class, everybody just has an F. Like I don't know why.
Well, at least we're all collectively failing. Nobody has to feel bad.
Grade on a curve. One person gets an F.
Again, nobody has to feel bad about themselves. That means we're all failing.
We're either all failing or all passing.
We pass by failing.
Yeah, and I'll talk about curves too and how we get a grade. All right, so like I promised, we're just going to review today, but I will hand back your exams and we can talk about them and just find them. So I just officially posted the grades. So let me hand back exams. All right, so let's just talk briefly about the exam. I was trying to get my stats on them. Just reminding myself. Okay. So overall, I was pretty pleased with the exams. So if you look at your score, so it's some sort of score out of 55. And so, right, you can convert that to percentage later. And so really, the points you care about are the average score was a 39.38. And then the standard deviation was about 10. And so what this means kind of for grading, and you can kind of at least guesstimate somewhat your grade or where you are in this is, so we'll do some quick stats real quick. And so, right, we have our average here, and we want some sort of normal distribution. And so generally, like, each standard deviation is like a grade or so. So, if you have, like, obviously a 49 or higher, that's like an A. And then, then we can subtract, so 29. So if I center this around a B, then we have C roughly, D. But then I was happy that no one was outside of this 2 standard deviation range. And then kind of the other note, so this is just kind of, right, a standard normalization curve with its deviation. But at the end, I normalize your grades anyways. So, right, if you look at the syllabus, everything is weighted by a certain percentage. So then I take, right, your total, and then we normalize it at the end. And so generally, right, it's a 100-level series. And again, like I mentioned, like, I'm pretty pleased with the exam. No one scored, like, super horribly. And so, right, my intention is to give probably mainly A's and B's in this class. If you struggle or maybe don't turn in assignments, maybe that'll turn into a C. But I'm not looking to, like, fail people for sure. And again, like, I'm trying to give mostly A's and B's for this class. And that's just historically kind of where the grades have fallen. So hopefully that makes you feel, a little better about all this. So it's all about kind of where you are in the curve. So again, right, you can kind of see where you might be. But like I mentioned, no one has such a low score that I'm, like, overly concerned about anybody. So I think everyone's, on a good pace. And so just, keep up the hard work for the rest of the year. Any other questions on just, like, kind of grading and?
So, based on the curve, is like a 34 or something?
Yeah, so like a 34 would be around like a BC average. And so that's going to kind of depend. It'll probably be more like a B range on that. But like I said, I'll tend to curve higher anyways at the end. It's all about the final grade. So, if you're doing well on your labs, like, that'll help kind of buffer you. If you haven't turned in your labs, so that could drag you down. So kind of keep that in mind. So yeah, an A is like anything higher than a 49, but for sure for this exam. But like I said, that window may widen. Because honestly, how I do it is I look at the grades, and there tend to be natural, like, breaks in people's grades. So then I can have a good cluster of, like, here are the A students, here are the B's. And if we have to, a few C's. But. And then, so as a department, science does not do pluses and minuses. That was just a decision that we made as a science department. So you don't have to stress about, the extra plus minus for your GPA. All right, so let's do some practice then. So I'm just looking at your homework. Let's just do a little practice here of this water plus diphosphorus pentaoxide gives us phosphoric acid. And so somebody had asked a question is the final cumulative? Like, will it have everything, on it? And so my answer is always, like, chemistry is cumulative by nature. And so, right, even though I may not test y'all formally on the final exam on, like, naming, you still have to know how to name and write your formulas, right, when it comes to writing these equations. So let's just try this one to warm up with, and then we'll keep doing some more practice from the homework or any other problems you want to look at for moles. Oh, and then of course, if you look at your exam and you think I added something funny or whatever, or didn't give you enough points, you can always ask me after class and we can fix that. So did we write out an equation? Are we still working on it?
Does it need to be balanced?
Yeah.
Okay.
Okay. Give people maybe another minute, and then yeah, if you want to put it on the board in a minute or two. I'll just prep some markers for you. You can do it on this board too. You want to start writing it on there? All right, so do we like it? Is it balanced? Is this what we got? Give me a thumbs up or. And so make sure that you know how to write everything so we can just walk through it. So, okay, we know water is H2O, diphosphorus pentoxide, P2O5, then phosphoric acid maybe was the only tricky one. And, oh, Did you have a question?
So like, wait, never mind. I think I just did it.
Yeah, this is a question I've had for a while. When you have polymatic ions in your, either your reactants or your products, are you supposed to break them up or are you supposed to keep them together? Or is that like, do you break them up or keep them together in certain cases?
Yeah, so that's like the tricky part, because sometimes like if you're just doing like a simple, so let's look at like one case, or like, right, if you did, we did the copper sulfate reaction, plus zinc to give us the, oh, sorry, I did that the backwards. No, that's correct. To give us copper plus zinc sulfate. So in that case, like, yeah, they stay together, and sometimes in like other precipitation reactions, they stay together. But then this one's kind of a weird one, and it's usually when there's some sort of like acid making thing, then yeah, it's like not as straightforward, so then you have to kind of break it up.
So when it's a polymatic ion is usually on its own, then it can be broken up?
Yeah, so usually try to see if it was kept together, but yeah, otherwise then maybe it was broken up, so.
Okay, that makes sense.
Yeah. And then, so this one, right, since this was a little tricky, right, since we have our phosphate on this side, but no phosphate on our reactant side. But then, different strategies for balancing. Maybe you could start with the phosphorus, put a 2 there, right, 2 times 3 is 6. So then you could puzzle out you needed a 3 for the water, and then it kind of falls into place. Other questions about just this one, or, yeah?
When do you put like those, like the physicals?
Oh, yeah, you should normally put that. I neglected that, so liquid. So this is solid probably, and then phosphoric acid would be aqueous. All right, let's look at some other ones. All right, so let's look at this problem. Let's look at 1 and 2, because it's asking us basically the same thing. And let's also look at what it's calculating. So we'll look at another example that's similar but different. And so this one is calculating the moles of O2 and 100 grams of O2 gas. And so in this case, we're talking about our element O2, so make sure you treat it as such, right, when you get the molecular weight of O2, so that it's going to be like 32 grams per mole. And this is opposed to any case where they're talking about individual atoms. But like I said, we'll look at another case. Let's see if we can do the rest of 1. So what do we get for this answer? What do we have to do? Does someone want to put it on the board for us? Giselle, do you want to put on the board for us? Come on, you gotta try it out. Where's your mole highway to help you? Someone else wanna, how do we start this? What do we do? And right, we could look at your mole highway too, right? If we forgot or dimensional analysis isn't clicking, right? What does it say to do? We have grams here. We're trying to go to moles. How do we do that? Yeah, so let's do that. So right, we have your chart out. If I need to get more, I can do that. I need to, just trying to find where my printouts are, but worst case, I can print out more. And so, right, also use your units to help you. So we have this is essentially your conversion factor, right? You're saying, well, for oxygen, we have 32 grams in 1 mole. And so now we're seeing how we divide. Again, right, that's what the chart told us, but now we can see, okay, yeah, grams is going to cancel. We're going to get moles on top. And so this looks good. And then let me fire up my calculator. So then we do 100 and divide it by 32, since again, right, it's asking about O2, our diatomic. And then we should get about, so we have 4 sig figs, so 3.125 moles. All right, questions on this first part? So then now let's keep this calculation, right? And now it's asking us, okay, well, we still have 100 grams of this O2 gas. So now calculate the number of molecules. So do you remember that conversion factor? It should be on your highway too. I'll write it out. So remember that was the Avogadro's number. So 1 mole is 6.022 times 10 to the 23rd atoms / molecules. But that is also on your mole highway. So take a few minutes. See if you can calculate that then. So what do we do? And it's actually pretty laid out nicely, because right, we have moles over here. We have our conversion factor that involves moles. So what should we do then? Or what does the mole highway tell you to do too? Angela, what did you do?
I didn't do it yet.
So what about, so look at this conversion factor. Does that inspire you here, right? So we started with, let's take this information that we got with, right? We already calculated moles. So the first half of this problem is done for us, right? Because same problem as before, 100 grams. Okay, we're at our safe space of moles. And so now if I look at this conversion factor, right? So we have a mole here. So let's flip that, right? So that moles can go on bottom, moles cancel, and then we have 6.022 times 10 to the 23rd molecules on top. And then, right, look at your mole highway though. Okay, so right, we're at moles, it's asking for particles, and then it's telling us, okay, multiply by Avogadro's number to get number of particles. And then looking back, oh, okay, yes, right, that's exactly what we figured out using our dimensional analysis. So then we can plug this in. And right, you can always mental math sanity check yourself. So we have 10 to the 23rd, oops, sorry. E to the 23rd, and times 3. So right, 3 times 6 is 18, so probably add another factor roughly. And so just like we expect, about 1.88 times 10 to the 24th molecules. Times 10 to the 24th, yeah.
Okay. Well, my calculator is getting a little bit bigger on those. All right, sig figs. I think you were paying attention to sig figs more than I was.
Oh, yeah, because you have the right factor. I just wanted to make sure. Yeah, as long as it's the right order of magnitude, that's always a good first step. All right, so let's look at a slightly different one. So I'm actually going to modify this problem for a second. And so first, start out with this, so number 6. So let's just start with that. So calculate the mass of 0.064 moles of C6H12O6. Yeah, or some sort of sugar at least. So before we do anything, we needed the molecular weight of a C6H12O6. So what do y'all calculate for that one? 180.066. Is that what other people got? So roughly, we could do it real quick, at least roughly speaking. So 12 times 6 plus 12, if I'm being imprecise, plus 6 times 16. So yeah, that looks really good when I get. So yeah, something like that. And so then what do we go from here? What does your mole highway say? What does dimensional analysis say? Michael, did you get an answer? Or what did other people do? Yep, so right, we just need to multiply by the molecular weight. So we're starting with moles. We have our conversion factor, right? So it's telling us, okay, it has 180 grams per 1 mole. So we can set up our dimensional analysis. And then again, right, look at your mole highway. It says the same thing. So if we want to go from moles to grams, right, multiply by molecular weight to get grams. So again, use that, right? It's your friend right now. That's why I gave it to y'all. So let's see, what do we get? So 0.064 times about 180. And so we should get about 11 point, we only have 2 sig figs, so I guess 12 grams there. And so let's take this question a little step further. And so now I want to know how many oxygen atoms are in here. And so right now we're talking about just single O, although I don't think you need the molecular weight for that. So how would you calculate that? Let's see if you can think about the strategy, right? Look at how many are in here too. So what's the strategy for this one? Any thoughts? Crystal, are you thinking something? Yeah, so the subscript is part of it. So what do you notice about that subscript at least? So it's a 6, right? So we can write a new conversion factor because we can say, okay, well, we have 6 atoms of oxygen, right, for every 1 C6H12O6. So now this kind of looks like moles maybe. And so if we have this 6-to-1 ratio, probably the easiest thing to do first is, well, let's just figure out how many moles of oxygen we have, right? So we have moles of our starting material, our sugar. And again, right, we have our ratio from our subscript. Okay, well, in our 1 mole of sugar, we have 6 oxygen atoms. So let's just set that up. So I'll just put, so determine moles of oxygen. So from our formula. And so again, right, we started with moles that was given to us. And that's moles of C6H12O6. We have our new conversion factor. So I'll put the sugar on bottom, so that cancels our 6 atoms of oxygen on top. And so then this will give us moles. But then if we want to figure out individual atoms, so how do we go from moles to individual atoms again?
What was the question again?
So how do we go from moles to atoms again? Yeah, multiply by which number? Yeah, Avogadro's. Exactly, right? So now we can multiply by our Avogadro, 6.022 times 10 to the 23rd, and that will give us individual atoms. So now we can punch through it. So 0.064, so that was moles of our sugar, so times 6, so that's atoms, moles of our oxygen, and so now times 6.022 times 10 to the 23rd, and so now we have 2.31 times 10 to the 23rd oxygen atoms. All right, let's look at some other ones from your homework. So let's try 7 and see how y'all do on that one. So calculating the mass of 100 trillion water molecules. So could you see that? So how's our problem going? So what do we have to do first here? So before we do that, though, because we have water molecules, so we have 1 times 10 to the fourth molecules of water. And so what do we need to go before we go to mass, though? We could look at our highway, right? Because we were given number of particles, so that's we're starting in a little bit of different place. And so we have to go to moles first. So then how do we go from particles to moles? Yeah, so that's our first step. So first, let's put it into moles. So dividing by Avogadro's number. So it's taking our factors. So 1 mole is 6.022 times 10 to the 23rd molecules. Right, so now we can get to moles of however much water we have. And so once we're at moles, though, then we can multiply by the molecular weight. So 18.02 roughly grams per 1 mole. And so let's see what we get then. So 1 times 10, 14. So then we get, right, this many moles. So times our 18 grams per water. And then, so what do we think about this? Can we see it? What do we think about that number? So yeah, I see some shaking heads. So yeah, that is way too tiny. You can only measure like, I think usually 1 milligram is like kind of your limit of what you can see. At least, again, just kind of generally speaking, like 10 to 1 milligrams. Let's look at some other ones. So I think you can do 8 then. So let's do some reactions. So let's practice the other half of your homework. Actually, let's do a not homework problem. Oh, never mind. Okay, I changed my mind. Sorry. Let's do a homework problem. So first, just start by balancing it, and then we'll briefly check before I send you off to A. So do we have coefficients? You guys can yell them at me. 4, 3, 2. And chat agrees with you, so that looks good. All right, so now that we have our balanced equation, see if you can do A now. So in the interest of time, so how do we work through this? Walk me through your setup. So right, we're at least starting with our 2.75 grams of aluminum. And then where do we have to go from here? Right, think back to those s'mores, right? We had to get in moles to compare, or like a recipe, right? You don't usually have gram measurements, although I guess you could, not to get too technical. But right, usually you're talking about cups, so kind of our moles. So we're at grams, so what do we need to do? Yep, of aluminum, and chat just agreed with you too. So 1 mole, and then aluminum is one of those ones I don't remember. Anybody help me out on that one? 26.98 grams, until I don't work with aluminum that much, so I don't remember it. All right. So where do we go from here? So again, kind of sanity check yourself. Okay, maybe you remind yourself, okay, where are we at? So this is giving us moles of aluminum, but we're trying to get to oxygen. So where do we go from here? Or think back to your s'mores too. Oh, chat saved you. So mole ratio. And so right, looking at our balanced equation, and so chat is telling me to compare our 3 equivalents of O2 to the 4 of aluminum, right? So we're just pulling it, our coefficients from our balanced equation. And so right, we have moles of aluminum on top, so now we need to put 4 moles of aluminum on bottom. We're trying to get to oxygen, so 3 on top. So that looks good there. And then, right, we can just remind ourselves, okay, well now we're at moles of oxygen, but we need mass. So what's our last little step here? Yep, so the molecular weight of O2, and chat also agreed. So that's 32 grams for 1 mole. Excellent. So now we can just multiply. So I like to just go step by step. You could obviously go across and then on bottom. So 2.75 divided by our molecular weights, okay, moles of aluminum, and then times our 3/4 ratio. And then, quick sanity check. Okay, we have less moles of oxygen. That's true. I punched it in correctly. And now taking moles of oxygen and multiplying that by 32. So then we should get, 3 sig figs, so 2.45 grams of oxygen. And again, that's diatomic oxygen in this case. Any questions on that one? All right, that's probably a good stopping point. I will share with you one of my secrets. So I didn't do it today, but usually, or sometimes I pull practice problems from this site, Everett Community College. They post a lot of practice problems, just free there. So I might post a link here so you guys can check it out. The only problem is I've noticed that sometimes their answers are wrong. So if you find an issue or you want me to check something, just let me know. That's not a big deal. Or if you're doing one, you say, hey, I wanted to look at this stoichiometry worksheet. Can you just look it over? I can do that. That's not a problem. But yeah, that's the one warning and you'll notice it in their key, because I think sometimes they like put in a wrong molecular weight, or, so I think you can catch it, but I'll just post that as a link, just so you kind of have more resources and practice problems for this topic. Because really all stoichiometry is practice, practice, practice. And so obviously I can do it really fast because I've done it like 1,000 times every day of my life. So all you have to do is practice, practice, practice. And again, right, stare at your mole highway. Okay, so let's take our break. I can start handing out the quiz anyways. So open notes, I would highly suggest having your little Vesper geometry chart out. Yeah, you're probably going to want that to help you. And any other notes on Lewis dot structures. And then, right, don't feel obligated to rush into it. If you need to go step and outside, take a break, whatever, go ahead and do that. I just wanted to get the quiz out in case people want to leave. And then, right, take your rest of recitation time to ask me questions, especially on any lab calculations or anything else. Again, just practice, 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 and just go geometry. Oh, yeah, of course. Oh, yeah, I forgot to make an announcement that we don't have school on Monday. So I'll send a Blackboard announcement, but yes, no school on Monday. So that means no lab next week, but Wednesday is a great makeup day. So if you have missed a lab, Wednesday is open time. We can fix it all then. So I'll just say that. And I'll post an announcement on Blackboard. All right, let me stop the screen.